What do we say in here? Help me out here. Isaac. Van der Waals. Van der Waals forces. Another famous Scotsman. Diamond. What is the type of bonding here? Covalent bonds. Covalent bonds. Now, ordinarily, you won't be told it's a covalent network. Ordinarily, you'd have to put a sentence in there to describe it. Covalent bonds in an extended covalent network. My writing's horrific.
Could you also say a lattice as well?
Yeah, lattice is fine. We usually use lattice for ionic compounds. It's traditional. Anyway, moving swiftly along, get past that one. Now, how do we go about answering a question like this? Well, if you're familiar with that table that we've just filled in, and you're quite familiar with the triangle, then we should be able to go round the triangle, starting with the particles, then the forces, and then some statement about the properties. That should take you through achievement and merit. And depending on how much detail you put in, you'll tick off excellent as well. Now, excellence, you have to just really be putting everything in there. That's what differentiates excellence from merit. It's not a different level of understanding, it's just completeness of answer, I think. Okie dokie. Magnesium. Okay. We'll start off with, we might just put a little triangle in here again. Particles, forces, structure, whatever. And then the properties. Props. We did props just now. Alright. Statement about the particles. Magnesium is made up of or consists of atoms. It's made up of atoms. Now we have to say a little bit about the forces between the atoms. So this is where you have to have some sentences to beef out your understanding of the forces. Now we've already used the forces holding the atoms in place are strong electrostatic forces, and this is where I'm a chemist, I'm not a teacher of English. This is a clumsy sentence construct, but the examiners are just looking for, they've hit that point. Might be a bit clumsy. Wasn't written by William Shakespeare, but they've got the detail in there. So the forces holding the atoms in place are strong electrostatic forces between the methyl atoms and delocalized electrons. I'm not really too happy with that sentence, but you get the hang of it. Okay. It's a sentence roughly that we used before. Now, I can reduce everything to a little triangle, but I do expect that you've got some knowledge that you can feed in there. There's something rather special about that metallic bond that we haven't talked about yet. The fact that it's just those loose electrons getting in between the metal nuclei and the attractions for the electrons and neighbouring metal nuclei is what holds everything together. But there's something rather special about the way that operates. It's quite different to when we were looking at, say, electrons around the nitrogen atom in ammonia. The electrons in the nitrogen atom in ammonia take up a very particular shape, don't they? They arrange themselves in a particular shape for various reasons. There's no arrangement around the metal ions as far as the electrons go. They're free to move. So what's the phrase that we use to describe that situation about those bonds? We talk about them being, sorry? Free, not free roaming. Non-directional, thank you very much, we've got it. We've used the term before. Inspirational. Now remember that. That's one of the bits of information you just file away inside your brain and don't forget it because you might need it. Metallic bonds are non-directional. Alright?
Should we also add in the properties of them?
Now, exactly. That's now, and the final sentence has to be a comment on the property. So it works, the system works. We've started with the particles. We've forced ourselves to say a little bit more about what the nature of those forces are, other than just to say metallic bonds. I mean, you could answer this question and say, yeah, it's metallic bonds, and yet they're non-directional. You could just say that. That'll get you achieved, possibly merit, but it won't take you all the way through to excellence. We'll be looking for you to flesh out the nature of that bond a little bit more. That's the important part there. Okay, so how are we going to... We're 2/3 of the way there. How are we going to clinch the deal by talking about malleability? We had a little picture to explain it before, but we've got to use words now. Essentially what's happening to the metal atoms in a lump of metal when you beat it into shape or when you draw it out into a wire, when we talk about ductility, it just flows, doesn't it?
Yeah.
I can't. Yeah, you're right. But we need to just say it a little bit more scientifically. Because they're non-directional, we'll leave it at that. You don't tie yourself up in trying to explain things in chemistry. There's only so far you can go to explain what's happening, and then ultimately that's just what does happen. So the easiest way to explain this is to say that the layers of atoms are free to move over each other. Now you might put a wee diagram in there to illustrate that. I've done another tutorial before where I've illustrated that very thing, the layers of atoms moving over each other, so you probably want to go back and maybe look at that. But there we go, we've gone through a process that's generated an answer. The bell's gone. Shove off, beat it.
Good, sir.